let me start our webinar today. And it is organized in a framework of informal community, which is called Atomic Scale Design Network, which has been created by myself in 1990 as a part of interface of Motorola to scientific community when the company realized they need much more fundamental science they can afford inside of the company. After my separation from Motorola in 2003, so I turned this into educational web portal, mostly connecting, having the new web pages from different people, professors up to from high-level professor to the young students with their personal view. And in fact, that's kind of linked to our speakers today. So once once I started the project on education and computational material science for high school, so I've been connected with our speakers today, and they inspired me of adding the webinar to Atomic Scale Design Network. So in fact, our Mansoor's family, Mubashir, Mehya, and Maryam, they have so much enthusiasm, they can drive anybody on, on their side, even if you start with your own ideas. So,
You're
they
very persuasive.
right, they are. And just a brief introduction. So, they are graduate students in Istanbul Technical University. Uh, they are fascinated with both experimental work and computation in gemology in jewelry industry. That's what inspired them, and we already mentioned this in our preliminary discussion. That is was kind of unusual because normally people, when they go in this industry, they're driven by a desire to become rich, and instead, this interest and fascinated field turned them into become a scientist. Mubashir is doing his PhD in physics, May in geology,
Just
and
started,
Maryam,
yes.
yeah, in mining engineering. But anyway, another kind of unusual that such a family collaboration in what they're doing together, combining both experiments and theory together, and I'm also fascinated how interested they go in depth of both fields, and this is very important for high quality applied science. And today they will be sharing with us their experiences both in experiment in calculation and their philosophy how combine these two. So welcome Mubashir, Mehya, and Maryam, and they also will be doing this presentation, all of them together.
Yes, thank you, sir. Thank you for the
Please
nice
start.
introduction. So I will be just going to start my PhD in physics very soon, so it's still not started. And hopefully we will interesting things going on over the coming years of this progress. So let's perhaps just begin. Okay, now we're all set.
Okay. So I would like to say hello and welcome to everyone. It is an honor to be presenting our views on the capacities of DFT on atomic scale materials design, and to hopefully create a bridge between the worlds of gemology and computational material science within this webinar. So we will be beginning by emphasizing the importance of materials in our everyday life, followed by the main problem in material science and how physics has come to the rescue, paving the way for the new era of atomic scale materials design. We will also present a work that we have done for designing a film coating which can actually filter high energy blue light using density functional theory.
Finally, we will consider how significant the impact of DFT can be in the world of gemology, all the way from how it can be utilized for reviving mines which have gone bankrupt to becoming an important aid in identification for gemological laboratories, and hopefully make it clear that it's time to start doing computational gemology.
So let's begin by considering these familiar words: Stone Age, Bronze Age, and Iron Age. It's not a coincidence that each era is defined by a particular material. In fact, I highly recommend these three books in which they define how important materials are for defining who we actually are in all facets of our life. I would even go further and say we are indeed our material.
That is so true. I mean, we are our material, but that begs the question, how many material are there? So this was an interesting question which Professor Brian Cantor asked and answered. He says, if we ignore the toxic, the radioactive, the rare, the exotic elements of the periodic table, we would still have 60 elements to play with in the periodic table. And if we consider that out of these combinations, the binaries and the ternaries and so on, and just imagine that we know those, we would still have this amazing number that we have 10 raised to power of 100 different materials which could exist. And that's a huge number. So if we consider that we know all of those binaries and ternaries, which is an overestimation because we really don't, the answer to the number of material that cover is this tiny, tiny, tiny fraction of 1%. So in fact, we really don't know anything about the possibilities in the world of material science. So we have just begun the road to discovery of material. So all of this amazing material, which are the building blocks of our civilization. I mean, just imagine everything that we have ever touched, everything that we have ever known, everything which we call the material around us are in that tiny, tiny fraction of 1%. So just imagine the possibilities. What could be if we were able to create these different combinations of those 60 elements in the periodic table, which are still unknown? I mean, maybe we could think about space elevators, maybe materials lighter than steel, but stronger than, there are still already very interesting material with these properties, but just imagine the possibilities.
Even better.
Even better, yeah.
I think it's beyond comprehension.
Exactly, exactly. I mean, Mehya is right. I mean, I don't think that we can even comprehend what is yet to be comprehended in terms of the possibilities. So we are in a very exciting era in the world of materials because the potentials are absolutely endless.
So considering the vast world of unexplored material, we have a problem. And the fact is that in most of material science, as Professor Donald Sadoway likes to put it, we are cooking and looking. If the material is already well studied, then experimental work is mostly on tuning the present formulation by adding a bit of this or that with smart guesses and characterizing again. But this approach is too slow, and even if we get lucky, the progress is just very expensive.
So Mariam's right. I mean, consider this binary system of boron and tungsten. Finding all the phases and characterizing each crystal in the system means individual experiments and many different compositions of boron and tungsten. But this is not a simple task. So even if we do manage to do it experimentally for a binary system, it gets very difficult for a ternary system or a system of more atoms.
In fact, it becomes so difficult that finding all the phases in a ternary system is equivalent to a good PhD thesis, which means at least 3 years of hard work for just one ternary system. Now, imagine combinations of 4, 5, or 6 elements. It becomes extremely difficult to know all the combinations. In fact, it's not a surprise that when we open a book which has documented phase equilibria, the most that we see is a ternary system. And it is a very, very rare to come across a quaternary phase diagram which is complete. So what is the solution? With this pace, even if we are lucky, it might require geological timescales of millions of years just to reach the 1% mark of all the material which can exist. So we have to look for smarter methods of finding novel materials. Actually, for survival of our species, we must.
That's so true. I mean, now let's look at what the beautiful words of Paul Dirac say. I mean, this is beautiful. Whenever I read this statement by Dirac, I feel these were so visionary people. I mean, just look at what he said in his paper in 1929. He says, the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. And the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble. This is so beautiful and true. I mean, Paul Dirac had envisioned, in fact, that theoretical calculations of all material properties is a possibility. But it's the complexity of the physics behind it, which means that it becomes extremely difficult. However, some things have changed since those days in 1929, which we will come to in a bit.
So Dirac was actually talking about the Schrödinger equation and the rise of quantum mechanics, a field of study which has truly revolutionized our understandings on every aspect of material science and made so much possible, from electron microscopes to spintronics, qubits, and so on. But the problem which Dirac referred to is still here. Application of the Schrödinger's equation for the purpose of computing materials properties is not easy at all.
However, what has actually changed a lot ever since the days of Dirac is our power of computation. Modern computers can handle what people couldn't even dream of back in 1930s. So, in fact, in the very early days of computation for quantum mechanical modeling, physicists started to create approximations to the Schrödinger equation and for the purpose of finding materials properties. And one of the most remarkable work in this regard was the work by the Rutherford student, Douglas Hartree, which is still used to this day, along with what he did with Vladimir Fock. So I think we are in for a very, very inspiring ride along the lines of what they started.
So over time, algorithms have become faster and faster with as little trade-off in accuracy as possible. And eventually, density functional theory was born. Today, by using hybrid functionals, it is possible to find material properties with a magnificent level of accuracy from first principles, especially when we consider the HSE functional for solid-state insulators and semiconductors. It really is amazing how precise these calculations are if the boundary conditions are assigned properly.
Yeah, so this comes back to what Professor Korkin just mentioned.
Yes,
garbage
absolutely.
in, garbage out. We have to be careful not to put in some garbage. Other than that, it's all perfect. So, in fact, when we look at the literature, especially over the past 15 years, the application of DFT for calculating many of the important material properties can be seen, and it has now become possible to bring together a bunch of atoms in our computers and set the required parameters, send it off for calculations in a supercomputers, and get everything from the electronic band structure to optical transitions, phase equilibria, catalytic behavior, thermodynamic properties, mechanical behavior, and even spectroscopic properties of the material. Now, the only problem with this sort of calculations is that they are very time consuming and they need a serious infrastructure in terms of the computational facility. So if anyone is interested in doing a comprehensive and detailed and interesting work in this regard, it is inevitable that they should have access to some serious supercomputers. And fortunately, there are many around who are willing to invest their resources on quantum mechanical modeling of materials. So I think we are living in a very inspiring age.
People are now talking about virtual labs and how the application of DFT can be automated through machine learning and artificial intelligence. There is a beautiful paper by Professor Cedar that talks about this idea in detail. And it is now possible to calculate phase diagrams of more than 70 binary phases in just 6 months with excellent accuracy in comparison with experimental work, which takes decades. I mean, that's truly inspiring. Yeah. In fact, DFT is even more successful than experimental work in many cases, where studies on metastable phases or ultra-high pressure conditions, such as the core of the Earth, because those are very difficult and sometimes even impossible to analyze in the lab. So in other words, we have entered a new era in the history of human civilization because for the first time ever, we now have a power to calculate most of the material properties before even stepping in the lab for any experimental work. And that means that we are in for a very interesting ride. And the future is looking very bright, as it is only now that we can truly unleash the powers of material science.
I think Professor Jeffrey Grossman at MIT puts this into perspective very beautifully. So I'm just going to quote what he said in one of his solid state chemistry lectures. He says, uh, we name the age we live in often by the element, by the atom, or by the material that was most useful at the time. So the Stone Age, the Bronze Age, the Iron Age, the Plastic Age, the Age of Silicon, and so on. As a material scientist, I love this. But I also love that we will never do this again, ever. We live in a truly unique age now, one in which we can realize Feynman's dream and put atoms wherever we want. The question is not, can we make it as much anymore, as it is, what should we make? We live in the age of atomic design. This is so beautiful. Yes. So he's absolutely right. In fact, I'm going to quote Professor Cedar as well, and because what he said in his lectures on quantum mechanical modeling, which is actually accessible through OpenCourseWare, MIT OpenCourseWare, his lectures with Professor Marzai, he says that if when we consider DFT, the problem is not as much how to do the DFT calculations, but rather what to calculate. So it is very important that materials engineers embrace such computational tools for propelling the material science field further than ever before. So I think there is great potential here, as many computational scientists believe, but there is a lack of fruitful communication between the experimentalists and computational scientists. So we hope that this bridge becomes stronger and stronger over the coming years.
Okay, so now let's investigate a small case study from a recent work we had done, which was inspired and encouraged by our dear Professor Kalash at IT. We wanted to create a coating which can absorb high energy blue light because, as you know, blue ray is proven to be more lethal than naturally occurring UV for our eyes. And we intend to show the effectiveness of DFT calculation for going all the way from atomic scale design to process design. So we chose to study rutile as it already has a band gap of 3 electron volts, and all we needed was making it narrower by a fraction of EV through playing with its defect chemistry and doping. Rutile has several advantages. It's inexpensive, possesses potential for high photocatalytic activity, and it can be coated in cathodic arc PVD, which is a fairly new Russian technology. So Professor Urgen's group at ITU have conducted some remarkable work regarding coating titania with PVD. Their work is also referenced below.
So when we check the literature, the paper by Saini in 2017 shows that the effective band gap of rutile can be slightly reduced by doping it with copper or iron in the rutile structure. So we thought, well, that might be an interesting option from an experimental point of view, but the problem is when we consider PVD, as shown here from one of our experiments in Professor Urgen's group, it is definitely not easy to incorporate a few parts per million of iron or copper into such a system. I mean, it would be quite difficult to do it. Perhaps a special cathode might be used, which would be extremely expensive, or maybe using E-beam or lasers to evaporate a few parts per million of copper or iron, or maybe some iron or copper complexes in gas phase. But all in all, we thought to explore alternative solutions because these are both expensive and very difficult to do. So what else could be done was the question.
Perhaps Feynman said it best. If we want to solve a problem we have never solved before, we must leave the door open to the unknown ajar.
So we have some basic requirements. Our dopant for the rutile for the purpose of blocking blue ray should be in gas phase at room temperature so that we can send it in a PVD chamber very easily and with great precision using electronic flow meters. It must be inexpensive and it should be easily diffused into the titanium structure.
So we looked at our lovely friend, the periodic table, and said, "Table, table on the wall, which is the fairest atom of them all?" She looked back and spoke, "The elements abundant in universe hold your vow. Carbon, nitrogen, sulfur, and oxygen are thy resolution after all." I replied, "We have faith in thee, wisdom, and shall follow thy trail of thought." So actually, this is a poem inspired by Disney's Snow White.
Our favorite, one of our favorite fairy tales, yeah. Especially the part they dig for diamonds. That's really fun. Yeah. So for an easy diffusion and high solubility of dopants in rutile, we should use either titanium or oxygen's neighbors. And since titanium's neighbors are not found in gas phase easily, we thought to consider oxygen's neighbors, in fact. And when we consider dope and co-dope systems out of these few elements, we have more than 100 different possible defects to investigate. So we embarked on this search. In fact, carbon seems to be offering great potential as well. So a study by Professor Lee's group back in 2017 has shown that carbon, which is positioned in oxygen side, can reduce the effective band gap to 2.74 electron volts, with the new allowed states very close to the valence band, resulting in absorption of the blue light to some extent. And there's also another interesting work by Bank, which have reported experimentally that carbon-doped rutile has caused the redshift in the absorption spectra and an increase in the photocatalytic activity. So we thought, well, this is interesting. We're on the right track. So let's go on.
Yeah, so after a couple of calculations, we found the density of state and band structure of carbon positioned in place of an oxygen with an interstitial hydrogen to be very interesting. So we thought to look at them even further. So what we did was we did a very precise calculation on this defect system, starting with geometry optimization using generalized gradient approximation, GGA. And oxygen was replaced with carbon saturated with hydrogen.
So every frame shown here emerges after calculating the interaction of every electron in the system with the mean field of all the electrons and nuclei through the above equation, and until self-consistent wave function is found. This process is repeated until the minimum energy of the system is found, and thus a precise density of states and band structure was plotted. So this calculation was actually done with Quantum Espresso, which is an open source code. So we highly encourage our fellow material science friends to try it out. It's fun. It's really fun.
So the UV visible spectra which emerges as a result of this defect was calculated using state-of-the-art time-dependent current density functional theory, using Professor Arjan Berger's kernel, which was developed only 6 years ago and includes electron-hole interactions.
Yeah, so the dielectric function was evaluated using the macroscopic electric susceptibility through perturbation theory. And finally, its complex part was converted into UV visible spectra. The results of these calculations made us very excited because it beautifully blocks the high energy blue light. And even more interesting is that the defect shows higher absorption coefficient as the energy of blue light increases while it transmits the lower energy blue light, which is like a dream come true for the purpose of this study. However, this doesn't answer if this defect is stable from a thermodynamic point of view or not. So if thermodynamics says no, then we have no right to consider this defect from an experimental point of view. So the work should, of course, move on.
Well, technically, we should have calculated every possible combination of defects by co-doping hydrogen and carbon to know which defects are most stable under which experimental conditions. But we got really lucky because Professor Ronchen's group have already calculated the defect thermodynamics of this system only a few months ago. Since we can't be in the oxygen-rich region during PVD growth due to the target poisoning problem as a result of excessive oxidation of cathode, we have only considered the defects which are most stable in oxygen-poor conditions. Now, they have shown that interstitial carbon plus vacancy, interstitial carbon alone, interstitial hydrogen, and our lovely carbon at oxygen site plus hydrogen interstitial are the stable ones in the order shown here. Given the potentials of the defect we have discussed earlier, we thought it's worth it to calculate the optical behavior of all these defects. Maybe we can still use it despite our defect of choice not being the stable one.
Yeah, so this is a very good example of what we were talking about in the informal part of this talk, because uh, if we don't consider the defect thermodynamics, then having the properties, the optical properties of a single defect is quite meaningless. So in this case, it was necessary to go further and see how the optical properties of the other ones, which are actually more stable, turn out. Because if they are doing an absorption in the red region or in the blue or in the green region of the spectra, then I mean, you should start over from scratch. So here is the result of investigating all the thermodynamically stable defects of this system. And the result just speaks for itself. I mean, all of these defects are exceptionally good. We therefore concluded that co-doping carbon and hydrogen in the rutile structure can block high energy blue light and even increase the photocatalytic activity. So this is a very exciting example of using DFT from our point of view. In fact, from here, we can move on and to design the process parameter, because again, Professor Cedar would be an appropriate quote here. As he says, it's not possible to model everything along the way, but it's all these bits and pieces of information which will help tremendously on the ultimate of how to make that a reality. So you have to consider what the process parameters are here.
So a tiny bit of methane in the argon atmosphere and trace quantities of oxygen inlet within the PVD chamber while using a titanium cathode should do the job. It's very important to know when to stop calculating and when to start experimental work. So trying to simulate the deposition and crystallization of rutile on the substrate might be far more challenging than trying it out experimentally, while knowing what to do is a lot easier to consider computationally. So Professor Cedar's views on this are quite important to consider for knowing the limits and the opportunities using DFT and molecular dynamics.
So I think let's switch gears now. And since the main purpose of this webinar is to talk about computational gemology and how computational tools can be used for the purpose of computational gemology. So we have given an example of how you're using computational material science in the world of materials engineering. But this is not happening in gemology. So we would like to consider that this is an interesting area which has sparked interest for a lot of computational work on diamonds. So there is this beautiful review by Professor Ghali, which mentions that some of these ab initio calculations which are done on materials used as a gemstone, such as sapphires, diamonds, etc. But these are not done. I mean, these calculations are currently not done for the purpose of solving problems which are important in the gem and jewelry industry. So you're usually focused on the electronic properties or the quantum computation possibilities and so on. So we would like to introduce this field of computational gemology and highlight how important computational gemology can be for the purpose of gem and jewelry industry. So we have used sapphire as a case study since it's a material we constantly do research on. But what follows is true for almost all of the gemstones. So here is a band structure of pure sapphire, which has an experimental gap of about 8.8 electron volts, with a valence band made up of p orbitals and a conduction band of s and p orbitals. So due to its wide gap, sapphire is transparent over a wide range of wavelengths, from 250 nanometers to 4,000 nanometers. So it's a very interesting material for lots of optical applications beside gemstones. It can be, I mean, when we consider its amazing high temperature and tribologic properties, it's almost difficult not to use it somewhere. It's such an interesting material.
So if we consider the reasoning behind color in most gem-grade sapphires, it's almost always due to the D-shell orbital, as it is shown here. For the case of ground state in titanium and iron co-doped sapphire, where the dopants are in adjacent aluminum sites, yielding a pleasant blue color in sapphire. So there is a beautiful work by Professor Napatalan where they have calculated the optical transitions of this iron titanium defect in sapphire using just GGA functionals and have found that an absorption should be expected around 620 nanometers, which is a good enough estimate for the experimental value of 570 nanometers, given the inherent inaccuracy of the GGA functional. So one could definitely do much better by considering hybrid functional in this regard.
So something important has to be considered here. We should note that even the slightest addition of an element inside the solid solution can change the bond length here and influence the energies of the d orbitals, even if the atom in question has no d orbitals in itself. And that would in turn change the response function, and it would also inevitably change the optical behavior of the material. So this is a nice example of what happens to the ground state band structure of iron titanium defect in sapphire when we add an interstitial hydrogen in its vicinity. They're not entirely the same. So the optical response cannot be the same. So the color shade cannot be the same. Everything changes as a result of the addition of that tiny hydrogen into the mix. Now, currently, in the gemological literature, there is a serious lack of knowledge when it comes to the interactions of defects and interactions of particular elements with the known defects which are important in the gem and jewelry industry. So I think this is a very good example of highlighting why we should actually do these calculations, because this is almost next to impossible to verify from an experimental point of view. I mean, I don't see any other way other than computation to find what can be the causes of many of these deviations in shade and color and so on, other than using DFT. So if there is a way, please do enlighten me too.
So here is another example for the case of doping chromium in alumina, which is commonly known as ruby, where again we have D-shell orbitals in the band structure. Professor Napatalong has done an interesting calculation with state-of-the-art HSE functional and found the absorptions within approximately 20 nanometers, which is quite good. One can even go further and calculate the fluorescence properties as well through the same procedure they have employed through plotting of the configuration coordinate diagram.
So it's quite fascinating to see how simple it has become to calculate optical behavior of defects ever since 2005. So, however, this doesn't tell much about the absorption coefficient, or in other words, we don't know how much of this defect is actually necessary for a particular color saturation.
Now, this is a very interesting article which was recently published in the GIA Journal of Gems and Gemology, written by Dubinsky, Sundberg, and Dr. Emmett, where they have taken the extremely difficult task of finding the absorption coefficient with respect to concentration, or in other words, for finding how much of the dopant is necessary to get the same color saturation. So here are nice swatches they have made as a result of the difficult experimentation of creating ion implant quality samples and analyzing the results. So this type of experimental research is beautiful and quite interesting to see that, for example, you need 5 to 10 parts per million of iron titanium to get a saturated blue sapphire, while you need 1,000 parts per million to get a saturated red ruby.
So that's a big difference.
Yes.
So now this kind of experimental work, although perfect and beautiful in every sense, cannot be done so easily when we are talking about samples which are heavily co-doped. So when we have these highly co-doped systems, this is where computation can shine very brightly. And there is a very interesting example by Professor Rare's group at Washington University, where they had used diamond as an example, and they had applied the Betz-Salpeter equation for calculating of the absorption coefficient in defects where nitrogens and vacancies are involved. And a small example is actually shown here, where they had calculated the amount of the defect necessary and the amount of the impurities necessary to create a particular color saturation. So in our work, we have seen that the influence and the possibilities with time-dependent current density functional theory are immense in this field as well. So it's not a difficult, I mean, it's not entirely easy set of calculations, but when we consider the alternative, which is the experimental way of verifying it, we are quite happy to do it computationally because experimental work would be extremely, extremely difficult.
Now, the question is, why does this matter? In other words, why should we even care? It is surely interesting to see why some gems have color and so on, but this really can't justify thousands of hours of valuable supercomputer time to be spent on studying such phenomena.
So we have two goals, which are the driving force for our research in this area. The first problem is that everything that is mined is not marketable. And many of these sapphires, which don't end up in jewelry stores, have a problem in their defect chemistry, which makes them unappealing. So in our travels to East Africa, we have come across situations where hardworking miners presented gems which did not have a market. For many of artisanal miners, this means no food on the table and ultimately leads to bankruptcy, adversity, and poverty.
So throughout time, gemstone heat treatments have been a reason why artisanal mining of gems is even possible. But the problem is that there are only a few standard heat treatment procedures which have been found mostly by trial and error, and they are only the treatments are only working for a few trace chemistries and completely fail on many other chemistries for sapphires from particular localities. And from this vantage point, we strongly believe that quantum mechanical modeling can change this, as we have seen in our heat treatment experiments, that DFT can answer questions which are deeply rewarding in this area. So we can even go further and say that such calculations will tremendously help gemological identification of the treatments, because most of the spectroscopy signatures of sapphire treatments are unknown and rather vague in the current literature.
So why do these problems even exist in the gem and jewelry industry?
Natural gems are crystals with highly co-doped elements. Sometimes even 20 elements might be present in different concentrations at the same time. So the number of possible defects is so much that it truly becomes complicated, and the defect chemistries and thermodynamics can be highly variable, depending on the locality, of course. We don't know the optical transitions of the many defects in such gems either, because if we did, then by using UV visible spectra, fluorescence, FTIR, Raman, and trace chemistry analysis of a gem, it must have been possible to even deduce the treatment type and even go further and have an estimate on the temperature, total pressure, partial pressure of gases, and the duration of the heat treatment, which can completely transform the sapphire industry into a trade which would be impossible to harm through unethical practices of not disclosing a treatment.
But this is not a simple job. It's much easier said than done. In fact, if we consider the simple example of an iron-doped sapphire, all of these defects and many more can occur.
So in the past, it was extremely difficult or even next to impossible to compute defect thermodynamics, as the amazing books by Kofstad and Kruger mentioned. But using the present computational methods with DFT, it is rather simple to deduce which of these defects is stable under which treatment conditions. In fact, if we consider the two examples shown here for an isolated iron and aluminum site or an iron-iron defect, the band structure of either case is considerably different. So we must know which of these actually occur. And the only way of knowing that would be, of course, to consider the defect thermodynamics. Now, it must be noted that the stabilities depend on the chemical potentials within the system. So even the most unlikely of such defects, for example, an iron in an oxygen site, would be quite stable under a particular set of conditions. So it's not possible to really say that iron is only stable when it is in an aluminum site. So there are all these different combinations where a particular atmospheric condition or a particular absolute pressure or a particular temperature makes that particular defect stable. And there is no way of knowing this precisely or accurately if we just proceed experimentally. And I think this is where the computational methods such as DFT can play an immense role. So why do I have confidence in saying that this is a possibility? It's because of this amazing pioneering work by Professor Bilge Yildiz at MIT. So again, MIT is a very good example of where they have integrated computation and experimentation. This is another beautiful example in this regard. So when we look at their work, they have studied doped alumina coatings and investigated how to reduce solubility of hydrogen in these alumina coatings for the purpose of reducing corrosion in nuclear power plants. So it's a totally different field. But it's very impressive to note that the Kruger-Wink diagrams that they have drawn as a function of temperature and partial pressure of gases for different dopants can actually pinpoint the defect chemistry of these crystals to an immense precision. In fact, I'm even going to go further and point your attention to the case where they have drawn the chromium diagram, the Kruger-Wink diagram for chromium. And it's interesting to note that as the partial pressure of oxygen increases and becomes closer to 1 atmosphere, there is that chromium in aluminum site +1, which is increasing in concentration. So if we recall, there was a paper by Professor Napatalong where they had calculated the optical transitions. And over there, they have also shown that this particular defect is one of the primary reasons for the red color of ruby. So is there a surprise that people prefer to heat rubies in oxygen-rich atmosphere? I don't think so. I think these calculations are a good example of proving the point. So it's interesting to note how defect thermodynamics and heat treatment parameters of sapphire for the gem industry can be actually linked. So I think the technique that they have applied for calculation of defect thermodynamics is quite inspiring. And there is absolutely no reason to believe that this sort of work cannot be done for the gem and jewelry industry.
In fact, now seems to be the best time to start doing these calculations on natural rubies and sapphires, because Dr. Palki's team at GIA has mapped out the trace chemistry of sapphires very well. And just imagine if we start doing DFT calculations on defects which can occur in sapphire from different localities. These calculations are indeed very challenging and time consuming because they may take decades before completion. And the picture that we can put forth is truly rewarding for everyone within the gem and jewelry industry.
So the heat treatment facilities will gain insight into how to do heat treatments on sapphires based on trace chemistry. And gemological laboratories will gain insight into how to detect those treatments as well, given that because of many of the optical phenomena in sapphire are still unknown. So we are also confident that while doing these defect DFT calculations, we will certainly have results which will be of importance not only to the gem and jewelry industry, but to many other industries as well.
So to conclude, we wish to invite computational scientists to consider studying the open questions in the world of gemology. And here is a roadmap that we would like to propose. That is, using the trace chemistry data, which has been mapped out quite beautifully by many of the gemological laboratories on almost a huge number of gems on different crystals. And we should follow that with the calculations on defect thermodynamics as a function of absolute pressures, partial pressures, temperatures, and so on. And go further and to calculate the optical behavior of the thermodynamically stable defects in such systems. And that will pave the way for heat treatment, designing heat treatments which are effective on not just particular set of trace chemistries, but hopefully on all trace chemistries. And that will also pave the way for gemological identification methods necessary to pinpoint treatments which are currently indistinguishable from one another using spectroscopic techniques. So, and those treatments are causing a major cause of concern. So this has caused the sapphire industry to create a basket called heat treatment and put everything there as if they're all the same, which they're not. So I think this is rewarding not just from the perspective of the gem and jewelry industry, but also, as Maryam mentioned, when we do all of these calculations, it means millions of defects. So it's impossible to calculate millions of defects and to not find interesting defects which are of use in other areas of material science or chemistry or physics or quantum computing and so on. So I think gemological questions are a good driving force for embarking on this very challenging and difficult journey, which otherwise people wouldn't really bother.
So we should also note that ethics dictates transparency in this field. It is quite easy to take advantage of the gem and jewelry industry by hiding discovery. But this must not be allowed to happen at all in any circumstance.
Absolutely. And everything should be published to avoid the chaos in the industry for its long-term prosperity and sustainability.
So in fact, we are even going to go further and say that this is a very nice roadmap for design of many optical material, regardless of the industry in question. So we would like to end here and perhaps continue the discussion using your questions and answer accordingly, and hear your comments, contributions, and so on.
And we would also like to express our sincere gratitude to our dear Professor Zuhal Professor Mustafa Organ, Professor Sarah Timur, for their very kind support and encouragements, and also the National Center of High Performance Computing of Turkey for giving us their valuable supercomputer resources. And also, special thanks to dear Professor Anatoli Korkin for encouraging science communication and also facilitating talks on computational tools, which is quite necessary in this era.
So thank you once again, and hopefully we will have interesting questions to continue the discussions.
Absolutely.
Let's start with the questions first. And there is one I see in their question and answer section.
Yeah, so Maryam has interesting questions here,
Yes.
which hopefully we will continue.
Okay, so should I begin, Professor?
Sure, please.
Perfect. Can you please go back to the slide of the iron doped sapphire and elaborate a bit more? Isn't iron in place of aluminum the most stable energetically?
Okay,
nice
that's a nice
question.
question.
Yeah, very interesting.
Okay, so what we were just trying to say is that these defects are all a possibility. It's not possible to say that some of these are the ultimate stable defects at all. In fact, so probably considering the world of gemology, many people consider that the iron in place of aluminum is the most stable. Well, there is no reason to believe that this will be the case for all temperatures and all partial pressures. In fact, by changing the partial pressures of different gases, you're changing the chemical potentials in the system. And it's that chemical potential which finally dictates where these defects become stable. And it's the same reason which actually makes it very difficult to do heat treatments on some of these gemstones, because then you don't know which of these defects are stable under which conditions. Then you just do the experiments and it's a big mess, because the observation that you get cannot be justified, and it will be completely different from a sapphire that you got from a different mine. So that's just what we were trying to say. And again, down there, it's a beautiful example of how the defect is extremely important in the band structure of natural. So having a precise idea of how to realize the interactions between the stable defect and its optical transitions and the defect thermodynamics, that circle. If we don't know that information, then we are pretty doomed if we want to do high temperature heat treatments on top.
Yes, indeed. Hey, let's move to the next question by Leroy Tang. They're mentioning that you use sapphire. First, they're thanking us, so thank you for joining us, actually. And they're asking, you use sapphire as an example. How about other gemstones that can also be improved by heating?
Absolutely.
Would you like to take?
Yeah, actually, the DFT calculations can be applied to any kind of gemstone, any kind of mineral, any kind of material. So your imagination is your limit.
Actually, the interesting part when it comes to sapphire or diamond, when it comes to heat treatment, is their capacity to withstand higher temperatures and higher pressures. So the reason why this becomes important in the heat treatment world and why we usually hear about heat treatment of, say, a sapphire or heat treatments on diamond, but we don't hear much about heat treatments in quartz, let's say. The reason is that these minerals like sapphire or diamond, etc., they can withstand conditions in the lab where we can make those defects move around, like they're sliding, they're skiing the solid state material in order to find their most stable
And
and
we
most
can actually control the dislocation densities, the vacancies formed, and also it's a little bit easier to work with.
But it's not impossible in other material at all.
Yeah.
So the same procedure that we have applied, that we have talked about here, can be done on any solid state material, and it doesn't have to be gemstone either. So the first example that we mentioned, it was for the application of creating a coating for perhaps your glasses.
Yeah.
So you know how to design a solid state material in order to block a particular wavelength, and those spectra are pretty important because the majority of the gem and jewelry industry is actually making money out of that spectra. So those fancy, beautiful colors are a product of the defects. And it's those defects. If you are able to control the defects, then you're able to control the color and so on. And how to create conditions for the material which are not so easy to take in, to manipulate their defects is another question. It's a more of an engineering question, but I think DFT can be applied. Yes,
it
it's
is
possible.
I mean, what we were looking for in the study that we had mentioned in the slide was to go for the optical properties, but it's not limited there. It can be mechanical, anything that you can think of about the properties of the material. So,
in fact, there is a very beautiful paper. Who has written it? I have forgotten, unfortunately. But maybe Mehya remembers. There was a paper where they had reviewed the application of DFT for finding the stable phase of iron in the core of the planet Earth.
That truly inspired me. Professor Berthold actually had published the paper, and it is truly inspiring. They had analyzed the different phases of iron within the core of the Earth, where the pressures are in gigapascals and the temperatures are above 6,000 degrees Celsius. So there are actually uncertainties at what the exact phase of iron is in the core of the Earth. And it was truly inspiring. I would recommend the paper very much. Yes, Leroy has also added that, have you studied tanzanite, for example?
No, we haven't, but
you really love sapphires.
We are pretty into sapphires. But the same can be done on tanzanite too. So in fact, I think tanzanite is a lot more easier to study in comparison to sapphire. Easiest of them all is diamond because you have an isotropic structure. In sapphires, you have an anisotropic structure. So the optical behavior actually depends on the crystallographic axis. But in diamond, you have an isotropic material. It really doesn't matter which way you're looking at it. So it becomes a lot easier to do calculations on diamonds. That's why we are considering diamond too. I mean, we are doing calculations already with Professor Uygen's group and under the guidance of Professor Zoaler on diamonds as well. So it's quite simple, and we are hoping that some of our work will be published soon for the purpose of finding the appropriate conditions in a CVD chamber and to map out the defect chemistries of the defect thermodynamics of these nitrogens and vacancies and hydrogens in these crystals. And we're doing this with a couple of friends at our Istanbul Technical University and the Material Science Department. And we're hoping that this would be an interesting work because we're getting lots of interesting calculation results. I don't want to give a spoiler now, but it will be interesting. Yes,
we'll keep you posted. Okay, Professor, would you like to add anything, or should I move next to the next question?
Yeah. Let's just first finish with questions first, please.
Okay. So this is an anonymous question. Why aren't miners investing in DFT calculations? That's a big surprise for me, they say.
Okay. So actually, some miners are investing in DFT calculations. So one of the most interesting people who are investing in DFT calculations is De Beers. I was first surprised when I heard this, but there is a group in UK where they are getting their sponsorship from De Beers in order to do DFT calculations on diamond. And it's not a surprise because diamond is such a well-studied material. Uh, but given that most of the work which is done for diamond and for defects in diamond are not for the purpose of questions in gemology, that kind of work barely gets attention in the world of gemology. But there are possibilities to do these calculations on a wide range of material. However, when we consider miners who are mining sapphires or other colored gemstones, uh, there aren't any of these there are very few multinational, maybe one or two large multinational companies who are capable of investing in such tools. So a lot of the mining is actually happening by artisanal miners, and they barely get their funds to get by the life with the minimum of the possibilities. So it's just an impossible idea for them. I think that will never happen in the world of colored gem industry, unless these large multinational colored gem miners get their attention to this, which I think it's unlikely. Because they are already making enough money. I mean, they don't really care that much.
Indeed. Yes, our next question is from our dear Professor Zohal Er. Thank you so much for coming and joining us.
Thank you. Thank you, Professor Zohal. Thank you.
So she's asking that, could you please tell us, will we produce smart sapphires? Or can I get your opinion on its application?
Smart sapphire.
Interesting.
There are many possibilities in the applications where you can have material which show interesting optoelectronic behavior. So we are hoping that down the road, it would become possible out of these calculations to find some of these defects which show interesting optoelectronic properties as well. But for the time being, we're just hoping, nothing is in sight.
What do you think, Professor Korkin?
There is still more questions. More general discussion.
We do have questions, I guess.
Okay, let's go.
So someone's asking that, should we trust the future of computational work at all? I mean, I guess they are experimental workers, but they're asking that how can we trust that? How can we proceed with that?
I think this is a good question for Professor Clark.
Well, it's
I mean, you're the professional in this field.
No, I mean, we just moving into discussions, which is kind of what we started at the beginning before. Is a very important point is to retain the professionalism in the field, so that people would study first the field in depth before they jump into something which is which considered to be useful. So they can play a little bit to get their own experience, but it's very important for the trust of both sides, experimentalists in people doing computation, that they are professional from both sides, and that is very important for the whole development of the area. And I really fascinated how you guys are nicely with enthusiastic, but with a caution, moving in both experimental and theory area. And this is a very important part. Like, for example, in experiments, you get everything in one shot, but fixing the conditions of, and you get integrated people in one experiment. In computation, you do the same, but you have to put atoms in a certain positions, which already kind of limit yourself to the sense how good is your initial guess, because when you do the optimization and you start from certain guess structure, your limit in your local minimum. The way to bridge this is actually, that's what computational community already doing in another field, is bringing the what is called artificial intelligence into the play. where you impose various smart algorithm, to find the global minimum and to combine local minimum together to get the overall picture for the materials. And that might be next next move for you guys to add it into your research. But definitely that has to be done after you get your PhDs, because you cannot do everything at the same time.
Hopefully.
In fact, actually, there is an interesting work by Professor Kringeli in Germany. Uh, they are using artificial intelligence coupled with DFT for finding these. So it's very interesting. They have these supercomputers which are 24/7 calculating and calculating and calculating, and they're creating these impressive diagrams of material trends. So they're getting these properties. Let's say these particular combinations of atoms can give us these particular set of properties, and then experimentalists can move from there. I think you're absolutely right. I mean, this sort of work is not possible without artificial intelligence into it, because uh, at some point, I mean, there is a limit to how much we can do manually. It has to be automated. It has to be smart. You're right.
We have a very nice comment and question from dear Ted Temelis, the legendary Ted Temelis, I must say.
So I must ask something before you ask the question. Ted Temelis is one of the most legendary people I have ever met. I mean, we haven't met in person, unfortunately, but we have the yes, we have the pleasure of being pen pals, and he's one of the best people in the world on the heat treatments of ruby and sapphire. So he has spent his life on doing this experimentally, and he's the only person who has actually documented the observations experimentally in great detail. And we're taking a lot of positive, valuable information from their work and for implementing it in the computational calculation. So I think he needs a very special respect for what he has done for the gem and jewelry industry.
Absolutely. Okay, so he's mentioning that the existence of commercial labs depends on the innovative gem treating techniques performed by experimentalists, constantly introducing new gem material in the market without warning. How computational gemology can help on this issue?
Okay, so I think this is a interesting question, because I think when we consider the power of computational material science, especially on creating these new gemstones, these new gemstone treatments, it would become impossible that people in the trade would be able to detect them without sophisticated knowledge or equipment for the for applying the findings from computational techniques. So I don't think that labs will go out of business if everything is discovered. However, I mean, the gemological labs, because they do the identifications for the sustainability and trust in the gem industry, which is very integral part of the trade. So without them, I think the trade will collapse in a very short time. But I think it will help them tremendously, because it will help both sides tremendously, the heat treatment community and also the identification community, because there is this misunderstanding, which I get quite upset about in the gem and jewelry industry by some people who are usually consumers. And that is the fact that they assume that people who are doing the heat treatment are trying to cheat them. That's not the case at all. I mean, I have barely seen anyone who has this intention of doing a heat treatment and hiding it from the public in order to, act as a vulture. That is very rare, and the few examples which exist should, not be able to do this. So how would we able to stop this vicious cycle of treatments being misused? That is only if we have a quite sophisticated tool of identifying heat treatments. And that will, I think, from my point of view at least, it's that the only way to do it would be to have a comprehensive knowledge of defect thermodynamics and also the spectroscopic properties of those defects. And if that is available, it would be impossible to heat treat something which which would be difficult to analyze. I mean, gemological labs should perhaps get more into the world of material science. That would be tremendous help, I think. Because many of the treatments in the world of gemstones are actually simple applications of material science. I think heat treatment community is material scientists. I mean, it really doesn't mean if they have a degree or not, because that's what they're doing. I mean, they're doing material science, so either intentionally or unintentionally. So I think that the opposite side who wishes to identify these treatments should be capable of the same understanding and even better understanding of the process. And that makes it necessary that material science becomes an integral part of the gemological labs. And I'm sure there are many, many, many people in the world of material science who would be more than interested. But it's just that this link does not exist. I mean, unfortunately, this link between material science and gemology is still quite sloppy. And it's usually between geology and gemology, which makes sense. I mean, because these are gemstones, you get them from the ground. Geologists are the first people to go to. But when it comes to treatments, I think material science has a lot more to say than geology, which of course absolutely crucial. I mean, we owe a lot and lots and lots to the world of geology for almost all of the gemology which exists today. So we are greatly in depth to the field of geology. But I think it's time to maybe pitch in some material science and physics and more chemistry, hopefully.
Indeed.
Yeah, I to the questions regarding constantly introducing new gem materials in the market without warning and how computational chemistry. Well, first of all, bringing the jewelry on the market without warning, it's a marketing trick. Has two elements. One element is to be ahead of potentially competitors. And the second trick are an effect of surprise, because when you come with a new gem, everybody wants a jewel, everybody wants to have it. So if you prepare the market for that, you might just lose the surprise, because I mean, somebody, oh, if you want to buy something, it has to be like a surprise, and you are the only one who have it. So that's two elements, ahead of their competitors and a surprise. However, how to use a computation, if these guys recognize that if they have computational tools in their labs and that help them to become the first ahead of the competitors, they will use the computational materials to be ahead of the competitors. As far as what you mentioned about the close to bankruptcy or something, one of the way, and that's also where computational material science can help, is to create the waste into the useful materials. So something which is look cheap and cannot be used in jewelry industry per se. So with a proper modification, with defects and others work where computational materials can contribute to understand how to create the useful material. First of all, it can add directly to the value of materials in their gem industry and jewelry industry. However, it also can link this market and this industry to others where the optical properties are important. So if you cannot sell it to the jewelry with modifying it property, you can sell it to some other industry where the optical properties are important, including, for example, lasers, electronics, and some other things. So that's hopefully is one of the ways
I completely agree.
to sell the computational material science to this industry.
There's just one point that I would like to add, Professor Korkin, to your statement. I mean, it is absolutely true that that element of surprise is sometimes helpful in the trade. But the gem industry has this tradition of not being so interested in being surprised, because in the past, sometimes not disclosing the treatment. And for example, let's say you have a very nice orange sapphire. Orange sapphires are rare. And then you create a process where you can create tons of orange sapphires from, let's say, green sapphires, then which are more abundant. Then you would be disrupting the market pricing, because if those traditionally naturally orange ones get mixed up with the new treatment, then the market gets a chaotic situation, because those people who actually invested in that expensive stuff are now losing money. and we don't want that to happen. So that's the reason why we say computational material science can help the gemological labs, because if you use the defect thermodynamics and the DFT calculations for creating new treatment, you can also use that exact same information for detecting that treatment. And that creates an equilibrium so that you can actually distinguish between this treatment, which is new, and the treatment which was conventional.
And it would actually maintain the equilibrium as well.
So yeah, I mean, you would have a parallel product so that it's cheaper, sure, but I mean, it has its own value. It has its own market. So there are these possibilities for which has happened throughout time. But there is also a problem which I would like to add as well. In the current state of the gem and jewelry industry, many treatments which are totally different from one another get mixed up in, and they're all called the same as the standard heat treatment. While when we look at the material science behind it, they're extremely different in the way that they cause the outcome. So I think the current state of the gem industry is a lot more dangerous than what it would be if the application of DFT starts. So I think what we're talking about here should not be an alarming bell for the formation of all of these surprising new materials. It is actually the way to do it, because if you do all of these calculations appropriately, then it would become possible, and apply material science extensively in the world of gemology, then I think it would become possible to create a much more transparent industry. Yes, I would absolutely. But that begs the phenomena of staying ethical. So no one should hide their findings. So once that starts to happen, things go the other way, and that is not a good way to do it. So staying ethical requires transparency, but it doesn't really have to be the way it is now. I think the gem and jewelry industry can go far beyond what the current status of the market. And there are many people who would be, I think.
So we already wait behind the schedule in sense of timing. So shall we still consider some? There is some more questions for discussion, or we may just conclude this the webinar.
So we can conclude the webinar, and we can answer the rest of the questions by email. So we already have the emails.
We truly appreciate the great participation, your kind messages, and also your.
Yes.
I'm just checking the chat messages, and thank you so much. Everyone's so kind. Thank you.
I mean, we especially like to thank our dear professors, Professor Sarah Timur, Professor Mustafa again. Professor Tolga Birkandan for coming. We truly appreciate it. Professor Zuhaler, of course, and also Professor Filiz Shahin, who joined us, and we would be very, we are truly humbled for their presence here. We
Absolutely, and we would also like to thank dear Professor Adolfo de Bastia for joining us.
Yes, indeed.
Thank you from all across the globe.
And also the amazing Ms. Dubinsky, the author of the paper which we mentioned. So thank you for coming. We hope that this webinar becomes a perhaps a starting point to think about the possibility in terms of the computational material science and how to link this with the present state of affairs in the world of gemology. Because gemology is filled with people who are very talented and people who are extremely smart. So I think once they get the idea that such tools can be used for the purpose of their challenges, sooner or later, these types of calculations will emerge, and I think we will all have a very interesting journey ahead. So this is something that we are definitely interested in doing.
We're passionate about it.
And hopefully we will have more to talk about in future on this topic.
All right, everybody. So let's conclude our webinar. So definitely has been successful, as we have seen it from the comment. Thank you very much. Thank you.
Thank you.
Thank you.
Thank you
so
much.
much. Wish you a wonderful day.
Bye-bye.
Bye-bye.